In this video, we'll explore the simulation for capacitors and dielectrics. We'll start by clicking on the Simulation tab. In step 1, we want to click the image of the simulation to start it. It will open a window which will ask us to run a Java program, which we'll download. And to show both the instructions and the simulation on one screen, I'm going to simply reduce the size of the D2L instructions and then include the simulation window. Step 2, to set up the simulation, we want to make sure the Introduction tab is selected. We want to ensure that all checkboxes on the right except for Electric Field Detector are selected. We're going to click on the red probe and hold the mouse button down and move the red probe to the top plate, and we'll do the same with the gray probe for the bottom plate. In step 3, we want to move the slider up halfway between 0 and 1.5, and we notice some effects here on the capacitance plates. So what happens to the distribution of the charges? The battery is causing electrons to be removed from the top plate, leaving it with a positive charge, and the bottom plate becomes negatively charged as the electrons pile up there. The area between the plates experiences an electric field due to the difference in charge between the two plates. There is also an amount of energy stored in the capacitor due to the electron buildup on the bottom plates. Consider what happens to the magnitude of the stored charges and electric field produced by them when the voltage on the battery is increased. What happens when the voltage on the battery is reversed? We can look at the battery and we'll increase the voltage a little bit more, and then we'll bring it down to 0, and then we'll reverse the direction of the current. The answer is the magnitude of the charges in the electric field increases as the voltage is increased, and the charges in electric field reverse when the voltage is reversed. The amount of stored energy rises to its maximum at both the maximum positive and negative voltages. In step 4, we want to click the green arrow labeled Separation and move the plates closer together. We'll have to reposition the red and gray probe so that they are touching the plates again. We may also need to change the zoom on the capacitance meter. If the capacitance level has gone off the scale, we would be clicking the zoom out icons to change the zoom level. Let's increase or decrease the separation, and we will give it some current. And I will zoom out a bit. The question, what happens to the charge on the plates and to the stored energy? What happens to the voltage? And finally, what happened to the capacitance? The plate charge and the stored energy increased. Those were these 2 meters here, but the voltage remained the same, and since the battery slider was left unchanged, the capacitance also increased. If we demonstrate this again, if we move the voltage to a certain level, as we change the plate separation, we have to move the probes. You can see that even though I'm moving the plate separation, the voltage is still reading 0.69. That's because that's what the battery is putting out. But the plate charge and the stored energy do change. The capacity did increase and decrease with the change in the plate separation. In step 5, we want to return the plate separation to as close to the original separation as possible. And then we want to stretch the plate area by grabbing the arrow and sliding out. So let's do that and see what happens. I'm going to just zoom out here a little bit. Question 5, once again, what happens to the charge on the plates and to the stored energy? What happens to the voltage? And finally, what happened to the capacitance? We get the same results as in the step above. The plate charge and the stored energy increased, but the voltage remained the same since the battery slider was left unchanged. The capacitance also increased. We can now go on to the second part of the simulation, the dielectric. And we'll click on the tab in step 1. We want to click on the dielectric tab. We want to ensure all the checkboxes on the right are checked except for the electric field detector. We want to move our probes into their position. That's step C and D. In E, we want to select Teflon as the dielectric material, and we're going to set the voltage of the battery halfway between 0 and 1.5. That's roughly about go more, a little bit less. There we go. Now, the double green arrow to the right of the dielectric will allow you to slide it into and out of the parallel plate capacitor. Let's slide the dielectric back and forth slowly a few times. And I'll zoom out here just a bit. I'll zoom out here just a bit too. In question 2, what happens to the values being measured? We see increases in the capacitance as the dielectric material is slid in between the plates, and all the other parameters and meters vary in accordance with the observations we made when we varied the plate area and separation in the first introduction. In step 3, we want to select the paper dielectric and move it in and out of the capacitor. We'll select paper, slide it in and out, and we want to notice to the levels to which the meters rise. And now we want to repeat this step with the glass dielectric. So now we have glass. In question 3, what do you observe about the relationship between the values of the dielectric, material's dielectric constant, and the measured values in this experiment? We see that the greater the dielectric constant, the greater the influence on the amount of capacitance, stored energy, and plate charge. Furthermore, the further any dielectric material is inserted between the plates, the greater the meter readings. We can now go on to the multiple capacitor simulation. So to set up, we'll click on the multiple capacitors tab. We'll ensure all the checkboxes on the right are selected except for the electric field detector, and we'll click 2 in series. We'll place the red probe at the top of the first capacitor's top plate and then the gray probe at the first capacitor's bottom plate. And we'll set the voltage between 0 and 1.5. Having done this, let's increase the voltage on the battery to the maximum level, then return the slider to the original position. We'll want to note the voltage on the voltmeter. So we'll do that now. There's maximum, and that's back to where it was. Now we're going to change the setting to 2 in parallel, and we're going to reset the probes on capacitor 1's bottom plate and top plate. And once again, we're going to increase then decrease the voltage on the battery. And I'm going to zoom out here. In question 2, what do your observations tell you about the electric field strength for the capacitors hooked up in series? The electric field strength appears to be greater for capacitors in parallel than in series. Now look at the textbook equations for capacitors in series and parallel. Do they make sense? Yes, because total capacitance in series only varies as 1 over the total capacitance, which equals 1 over the capacitance of the first capacitor plus 1 over the capacitance of the second capacitor, and so on, while total capacitance in parallel is simply the sum of the capacitances of the individual capacitors. The total capacitance is equal to the capacitance of capacitor 1 plus the capacitance of capacitor 2 plus the capacitance of capacitor 2, and so on. I hope this video was helpful in explaining the capacitors and dielectric simulation.